Good morning. So we're now going to start the last big area of the course, the last quarter. This basically is called modern physics, which is a bit of a misnomer because what we're going to be doing is material that has been discovered since the early 1900s. We still call it modern physics as opposed to what we typically call classical physics, classical mechanics, classical electricity and magnetism. But it's really not as modern as physics could be. There's been a lot of development since this, but it's still called modern physics. This particular section is an area that was developed by Albert Einstein, as I said, in the early 1900s. And this brings us to section 28, which is entitled Special Relativity. So, up until this point in the semester, we have been talking about electricity and magnetism, which we might refer to as classical electricity and magnetism. And if we took all of the results that we have developed in terms of the electric field and the magnetic field, like Coulomb's law, electromagnetic induction, the force or the magnetic field created by a current, and put those all together, the electric and magnetic fields could be described with four basic equations called Maxwell's equations. Last semester, we spent just about the entire semester looking at classical mechanics. Whoops. Which, as we saw, could be summed up with Newton's laws, the three laws of Newton. Now, in the early 1900s, Albert Einstein was looking at these, Maxwell's equations and Newton's laws, and what he noticed was there was an inherent contradiction between these. What he decided was that one of them, well, if not both of them, but at least one of them had to be changed. Now, if it were up to you, which one do you think you would want to change, and which one would you want to, say, leave the way it was? Newton's laws, very commonsensical, describing things that we see all the time. They do a very, very good job of describing the motions that we see all the time. Maxwell's equations, very mathematical, describing things that you really can't even see, the electric and the magnetic field, well, except for electromagnetic waves, which you literally do see. But for the most part, very conceptual things. For me, I would assume that if one of these had to be wrong, I would assume Newton's laws were right and that there was something wrong with Maxwell's equations. But what Einstein did was, he said, well, he thought that Maxwell's equations were probably right and that there was something wrong with classical mechanics with Newton's laws. Now, this is not to say that Newton's laws are just wrong. We obviously know they're not. They do a very, very good job of describing things that we see on an everyday sort of scale, everyday kind of motion. So we know they work very, very well under those circumstances. But what he said was that perhaps under certain extreme situations that they needed to be modified. And that's what he did. So that's what we're going to talk about. What Einstein said was that when we look at something, when we look at the motion of something or what something does, we need to consider where this thing takes place, where something happens, in addition to when it happens, and we need to put these things on a much more equal sort of footing. So, for example, when we describe where something is, we might use the coordinates x, y, and z. When we describe when something is, we describe the time t. And what Einstein said was we need to put these into a more equal, equal footing where we need to start thinking about the universe, say, as a four-dimensional object, a four-dimensional space-time, rather than just as three-dimensional space that seems to be progressing in time. We need to look at it more as a unity of four dimensions, which we'll refer to as space-time. Now, when we talk about a point in space-time, in other words, when we describe something in space-time using these coordinates, we're talking about something that occurs at a particular place at a particular time. So this four-dimensional point we'll refer to as an event. When we talk about an event, we mean a specific point in four-dimensional space-time that occurs at some place at a particular time. So, for example, you just pick whatever you want. Say the execution of Marie Antoinette. That's something that occurred at a particular place at a particular time. Other things occurred at the same time in different places. Other things have occurred in the same place, but at different times. But that particular event occurred at a particular place at a particular time, so that point we'll refer to as an event. Okay, now, in order to describe these coordinates, we need a coordinate system. So the question arises as to what coordinate system should we choose? Is there a special or particular coordinate system that is better than another coordinate system? Well, last semester we were free to choose whatever coordinate system we wanted. We could choose a coordinate system with, say, x is the horizontal variable, y is the vertical variable. If we wanted, we could choose y as pointing down. We could choose x as pointing to the left. We could pick any sort of orientation we wanted. We could put our origin anywhere we wanted. For particular problems where we were dealing with an inclined plane, we might actually have the coordinate system tilted so that x pointed down the incline as opposed to horizontal, and so x might have horizontal and vertical components, and likewise with y. We were completely free to do that. Well, the fact is that we are also free to do that with relativity also. We can choose our coordinate system with a whole lot of freedom as well. We can choose our axes pointing in different directions. We can choose our origins pointing in other directions. And there's actually another freedom that we'll see that we have in choosing our coordinate system for special relativity that we actually didn't have, or we didn't really think about when we were looking at classical mechanics. Now, before we actually start talking about a particular reference frame, I want to look at a little experiment. Let's do a little experiment. What I want to do is I want to choose two events, and I want to ask, what is the distance? What is the spatial distance between these two events? And I want us to look at them in two different reference frames. Oh, I'm sorry. Let me. When I talk about a reference frame, that's just a term that I will use to mean coordinate system. So, a coordinate system we think of as axes like x, y, z, and now t, so an x, y, z, t axis. A reference frame, just another way of saying coordinate system. My reference frame would be my coordinate system. Your reference frame would be your coordinate system. All right, so let's do a little experiment. I want to make two events occur, and I want to talk about what is the distance, the spatial distance between those two events. Okay. All right, so here I have a 2-meter stick, so from this point to that point is 2 meters. I'm going to make two events, and these events are going to be snaps of my fingers. Those events will occur at a particular place, at a particular time. What I want to ask you is, how far apart in space are these two events? Okay, ready? So here we go. All right, so you hopefully would say those two events occurred 2 meters apart. So one event here and there. I hope you would agree those two events were 2 meters apart. But I would say that those events were at the same place. They occurred at the same place because, where were they? They both occurred right here at the end of my arm, right like that, and right like that. Now, I was walking past, but to me, those events occurred at the same place. Now, this is a little odd. You would obviously say 2 meters apart. Now, how could I do that? I'm moving. But I want to say that my reference frame is a moving reference frame. My coordinate system is a moving coordinate system. And in my coordinate system, those two events took place at the same point in space. There was a time difference, obviously. They didn't occur at the same time, but they occurred at the same place. Now, obviously, you'll say, well, that's not really fair because you're standing still. The meter stick is 2 meter stick is standing still, and I'm moving. But to my perspective, and this might seem a little odd, but to my perspective, I'm just staying in place. My legs are moving like this, like I'm walking, and the building is moving past me. Now, obviously, that sounds a little ridiculous, but to my perspective, that's kind of what it looks like. I'm standing still, or my legs are moving, and the building is passing by. Is that really fair? Well, you say, well, obviously this is standing still, but are we really standing still? Is this building standing still? Well, we know we're on the Earth. The Earth is rotating, so obviously we know the building is not stationary because we're on a rotating Earth. The Earth is rotating, or I should say, revolving around with the moon. Not a great big motion, but a motion anyways. It's going around the sun, revolving around the sun. The sun is revolving around the center of the galaxy. The galaxy is moving through the rest of the universe. So obviously, even this building is not stationary. Who's to say who or what is stationary and who or what is moving? So, the important point is that a reference frame, or the coordinate system, could be a moving reference frame. So we could have moving reference frames, and when I say moving, I mean moving relative to another reference frame. To say that anything is absolutely moving or absolutely standing still is something that we really can't do. So, with that idea, Einstein based his theory of special relativity on 2 postulates. Now, what is a postulate? Like the postulates of Euclid, they're like assumptions. They are something that cannot be proven, but we'll assume that they're true and then see what sort of results come out of these assumptions if we assume they're true. Alright, so here we are, the postulates of special relativity. The first postulate we'll refer to as the relativity postulate. And it states, all the laws of physics are the same in every inertial reference frame. So what does this mean? Well, we know a reference frame, we just mean coordinate system. Inertial, I'll come back to in just a second. And what the rest of this says is that all the laws of physics are the same in any reference frame. So, let's take a look at what that means. Alright, so let's imagine we've got 2 reference frames. In other words, let's imagine maybe we've got 2 rocket ships here. And one of these rockets is moving at some speed v relative to the other rocket ship. So, in some perspective, we might say this one is stationary, while this one is moving in that direction at v. But in this astronaut's perspective, their rocket ship is stationary, and what's happening, this rocket is moving that way at a speed v. Now, the first postulate states that in any inertial reference frame, now, reference frame we know is a coordinate system. So, one coordinate system, another coordinate system. What is an inertial reference frame? An inertial reference frame basically means a non-accelerating. A non-accelerating reference frame. In other words, a reference frame that is moving at a uniform speed. Now, I'll come back to that in a second. All the laws of physics are the same, which means if this astronaut, let's say maybe call this astronaut A and this one B, if astronaut A were to do some experiment and astronaut B were to do the same experiment, the results that A and B would get had to be the same. The results of any physics experiment could not depend on what this speed v was. There's nothing that they could do short of just looking out the window and seeing the the other rocket or something, there's nothing that either one of them could do that would tell them that they were either stationary or that they were moving at some uniform speed v. Nothing that they could do. Any law of physics had to be exactly the same in each of these reference frames. Now, why is it an inertial reference frame? Well, if one of these were accelerating, that is something that could be detected. Now, maybe you've noticed that if you've been in a car and you're driving a car at a uniform speed, if you start to speed up or slow down, you can tell when you're speeding up or slowing down. When you speed up, you feel like you're pushed to the back. When you slow down, particularly abruptly, you feel like you're pushed forward. You kind of feel the acceleration that way. So an inertial, if you were in a non-inertial reference frame, in other words, an accelerating reference frame, that is something that you could detect, and you could actually figure out what your acceleration was. So, in order for them not to be able to determine anything about the motion of their reference frame, we need to look at inertial reference frames. Now, this is something that you might have actually noticed at some time. Maybe if you were sitting in a car or a bus or a train or something like that that had another car or bus or train nearby, and you might have noticed that this other vehicle started moving. And initially you couldn't tell. Were you standing still and the other train was actually moving, or was the other train standing still and you were the one that was moving in the other direction? And maybe you were a little confused initially. You couldn't tell which was which. Well, that's kind of the basic idea, that there really isn't a difference. You going one way and this train standing still, or you standing still and the train going the other way, there really isn't anything that could tell you one way or the other, until eventually you can see, well, either you're moving through the landscape, or the other one is gone, pulling out of the station, or whatever. But the basic idea is that if you're in an inertial reference frame, there is nothing that can be done in that frame to determine what kind of motion you have. There is no absolute motion. So that's the first postulate of relativity. And there is nothing here that Isaac Newton would contradict. He would think that this certainly sounds reasonable. There's nothing here that contradicts any of Newton's laws. Okay, now what about the second postulate? Okay, the second postulate, sometimes referred to as the speed of light postulate, states that the speed of light in a vacuum is always measured to be c, 3.00 times 10 to the 8th meters per second. Now let me emphasize again, this number, the speed of light in vacuum, is going to be something that we will see over and over again. So this is a quantity that I will expect you to remember, which means if you don't remember it, you will need to put it down on your card for an exam. But I'm not going to give it to you, and you won't have it for a quiz. So even for a quiz, you've got to make sure that you remember that. 3.00 times 10 to the 8th meters per second. This postulate is what comes from Maxwell's equations. If you remember the equations that describe electricity and magnetism, when Maxwell put them all together and solved them for the speed of electromagnetic radiation or electromagnetic waves, what he discovered was that the speed of those waves turned out to be, if we remember, that 1 over the square root of epsilon naught mu naught, turned out to have this value. But the point is, there was nothing else in those equations that had any effect on what that speed was, other than if it was going through a medium or something like that. We're not talking about that in a vacuum. The speed of the radiation is always 3 times 10 to the 8th meters per second, regardless of anything else. Now, this is very, very strange if we really think about what's going on here. So let's think about what this means. Alright, so let's imagine we've got a person here and a person here, and this person throws a ball to this person. Let's imagine this person throws the ball at, let's say, 2 meters per second. How fast does the ball approach this person? When this person catches the ball is approaching that person at 2 meters per second. Okay? Not a big surprise. Now, let's imagine that this person here is running toward this person, let's say at 3 meters per second. So they're running along, and now they throw the ball at a speed of 2 meters per second relative to them. So they're going to throw the ball just as hard as they did before. Now, how fast does the ball approach this person? Well, this person's running at 3, throws it at 2, so the ball is going to approach that person at, what do you think? 5 meters per second. Does that sound reasonable? The person's running at 3, the ball is already moving at 3 meters per second, the person throws it at an additional 2 meters per second, so how fast does it approach this person? Well, it's going to be 5 meters per second. Okay, that certainly seems reasonable and makes sense. Well, now, let's look at a slightly different problem. Let's imagine, again, we've got 2 people here. But now, rather than throwing the ball, let's imagine this person has got a flashlight. And this person turns on the flashlight, and light comes out of the flashlight and approaches this person over here. Well, according to Einstein's postulate, how fast does this light travel? Well, it travels at 3 times 10 to the 8 meters per second. How fast does the light approach this person? Well, it approaches this person at 3 times 10 to the 8 meters per second. This person measures the speed of light. This person measures the speed of light 3 times 10 to the 8 meters per second. Now, let's imagine this person runs towards that person, and let's imagine this is a very fast runner, and this person is going to run at, let's say, 1.5 times 10 to the 8 meters per second. Okay, very, very fast runner. So he's running this way at 1.5 times 10 to the 8, and again shines the flashlight. The light leaves the flashlight at 3 times 10 to the 8 meters per second. The light approaches this person. The question is, how fast does the light approach this person? Well, obviously, this person is running at 1.5 times 10 to the 8. The light leaves that person at 3 times 10 to the 8. So we assume the light approaches this person at 4.5 times 10 to the 8 meters per second. Except that's not what happens. According to the postulate, the speed of light is always measured to be 3 times 10 to the 8 meters per second. So if this person measures the speed of light, they will still get a value of 3 times 10 to the 8 meters per second. Well, this is very, very strange. This person measures the speed of light at 3 times 10 to the 8 meters per second. This person measures the speed of light as 3 times 10 to the 8 meters per second, even if this person is moving at 1.5 times 10 to the 8 meters per second. This is very, very strange. This doesn't look like the previous problem at all. Maybe this person moves at 2 times 10 to the 8 meters per second, or 2.5, 2.9, 2.999 times 10 to the 8 meters per second. Well, not quite 2.999. The speed of light is actually 2.998, I think, to 466. So maybe not 2.999, but let's say 2.997 or something like that. Still, the speed of light as measured by this person will be 3 times 10 to the 8 meters per second. So we cannot just add things like this. Something is very different when we're actually talking about light. As I said, this is what comes from Maxwell's equations, and this is really what seems to contradict Newton's laws. Newton's laws would not agree with this. Newton's laws would say the speed of light would have to be 4.5 times 10 to the 8 meters per second. So somehow, here we are deviating from Newton's laws, but let's keep in mind, we're really only talking about deviations occurring, or anything that's noticeable, when we have people running around at 1.5 times 10 to the 8 meters per second. When we have things moving at very, very high rates of speed, up near or around or considerable fractions of the speed of light, 3 times 10 to the 8 meters per second. Now, to get a quantitative idea of what's going on here, we are going to have to come up with some way of measuring time intervals. And we need to be able to measure time intervals very, very carefully. Basically, we need to do something that's going to follow the postulates in our definition of measuring time. So let's think about that. Let's imagine that we can come up with some kind of clock or some kind of way of measuring time intervals that will obey Einstein's 2 postulates. Well, here it is.